Let's give a round of applause for Microsoft. Thank you for everything they've done for us. Well, again, we have a great session, lots of great content, a lot of amazing demos, if the demo gods are with us, that is, of course. Kind of start off at the beginning. My name is Tony Sanchez. I'm with Citrix Systems. I work on the Worldwide Alliances team, specifically focusing on Microsoft integration, scalability testing with XenDesktop, with System Center Configuration Manager, with VMM, pretty much the whole 9 yards, as well as Hyper-V. Over to my left, I have the gorgeous Garrett James. Garrett, tell them about yourself.
Good morning, everyone. As Tony said, my name's Gareth James. I'm a senior consultant with Microsoft Consulting Services based out of Canberra, and I'm primarily a virtualization and deployment specialist. Excellent.
And then over to our far left, we have Nathan from HP. Nathan, kind of raise your hand, show everybody your lovely face. We also have a special guest joining us remotely, who you'll hear from very soon. Just out of show of hands, let me know who walked in this morning at about 2 a.m. from the party. 3 a.m. If you walked in at 3 a.m., stand up. Oh, man. 4 a.m.? Who just walked in right now from the party? All right, so if there's anybody that walked in at 1 o'clock in the morning, stand up and came here.
Got a bunch of early birds here.
A bunch of early birds. It must be good stuff. Okay. Well, that kind of puts a kibosh in what I was
Yeah, I
going to
know,
do.
but it actually explains why they're all here, right?
Yeah, that's good. All right, so toss them out to some people. Just show hands. Who wants something free? All right. Here's $5 coming at you. I'm not condoning you should gamble, but if you do win, I want 10%. All right. Just to show up, thanks for coming out here early this morning. We appreciate it. We know you got a lot of other things you could be doing, but thank you anyway for showing up. And I guess we'll go ahead and get started. Add the mouse clicker. Danny, did you hit anybody up there? Excellent, excellent. All right, looks like we're all out. So we're going to go over a little bit of an agenda today. Some pretty interesting stuff. The information we're talking about for this particular session is really different. This is not what I would call your average scalability or your average architecture. We're taking a very different approach, and with that in mind, we're presenting a much different set of data. That's a result of a three-way go-to-market reference architecture we did. Again, that's with Citrix, Microsoft, and HP. So we'll go through a little bit of the architecture, talk more about some of the results we got from a single server scalability perspective. We'll also talk about large farm results from 2,000 desktops. We actually really tested technically about 2,320, give or take. But we'll just kind of keep it easy and say 2,000. And then at the end, if there's time, we'll definitely go through a little bit of Q&A. So we'll go ahead and get to the next slide. So we're back again, the three amigos, Citrix, Microsoft, and HP. We did a reference architecture last year on a very similar set of hardware, but yet we took a different approach this time around, and you'll see through some of the results that it's unique. And there's a lot of things that make it unique in that sense. We realized that one of the biggest things that's probably crossing everyone's mind is cloud, whether it's private or public. And oftentimes, if you think about when you're building an architecture, you don't always have the ability to build a 5-star environment. Sometimes you need to build a 2-star environment given the architecture and the hardware that you have in place. So we're kind of taking that approach to saying, well, how can we build a great resilient architecture leveraging all these components if we don't have 5-star hardware, or if we don't have 5-star capability to do HA? So we're kind of taking a really good approach and showing we can still have great setup and great communication with all the components, XenDesktop, Hyper-V, and again, the Blade system we're going to talk about from HP. So I'm going to have to use the mouse on this one because we had a little bit of a PowerPoint animation thing. So what do we mean by it's the big one? Kind of let someone tell you about it.
You went and did it. This is a big one.
So it's a big one for us because we've never done a scalability test this large, leveraging all these different variables. And when I mean different variables, we're talking a huge amount of things that have changed. Not just with XenDesktop, but as Gareth will talk about, Service Pack 1, which includes dynamic memory. So we'll go into some of the things that we did do in this particular scalability test. And here's some of the things we talked about and we wanted to challenge as we went through this scalability design. We wanted to make it what we call a simple or poor man's VDI, in the sense that we want to make it easy to replicate. All of these particular bullet points you see down here are things that we did in fact do and are mentioned in that link at the bottom that is pointing to the reference architecture. The whole objective was to make an out-of-the-box experience for 2,000 virtual desktops. Nothing that we did, whether it's hardware, software, regardless of what it is, was tweaked. This is standard, out the box, next, 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 done. So there's absolutely nothing we modified. And with that in mind, the idea is that it should be easy for someone to go ahead and build and repeat, given they have the right infrastructure and setup. So we're going to switch over here to the next PC. I have a presenter that's actually dialing in live from Houston, Texas. His name is Kirk Mazur, and he's from HP. Kirk is the brains behind the hardware design that we have for this particular reference architecture, and he's a great resource. He's also a Citrix technology professional, so not only does he know the HP hardware inside and out, been with HP for a long, long time, I believe even into the compact days, but also knows our core software as a whole, so he's very, very knowledgeable. Do we have audio over on laptop over here? Wait just a second for him to switch over. Brilliant. Okay, Kirk, can you hear us on the audio at the moment right now?
I can hear you. Can you hear me?
Excellent. Everybody say good morning to Kirk. It is very, actually afternoon actually in his time zone. Morning for us. Kirk is doing a special appearance, allowing us to borrow his time to go ahead and present this information to you. Kirk, so if you can, just let us know when you'd like me to advance to the next slide, and we'll go ahead and skip forward.
Okay, hopefully you're on the slide with the car and not the pretty girl.
Yes, we are. We are.
And my ugly face. Good morning, everyone. We're going to talk a little bit about the hardware we used and the configurations that are all based on the HP Citrix Microsoft reference architecture that's published at www.hp.com/go/cv. All our reference architecture information is out there, and we used what we built that to build this environment. You can go to the next slide, Tony. Basically what we used were two HP C7000 chassis. We used 20 BL460 G7 blades as our VDI hosts. Each of these had 96 gig of memory, 2 hex-core processors, and each box supported 120 users. We also used 4 BL460 G7s as our management and PBS hosts. We did install PBS to bare metal. These boxes both had, again, 2 hex-core processors, a 48 gig of memory. For the storage side, we took a slightly different approach. We used 2 HP 600 modular disk systems as direct attached storage. There is no SAN in this environment. It's very contained, very low cost for storage. The idea being with non-persistent VMs, there's not a lot of information to maintain, so why put it on an expensive SAN? You can go to the next slide, Tony. As we said, this is built on our reference architecture. And the idea behind the reference architecture is to create a pod type environment that you can simply replicate over and over, knowing that it will support X number of users. And this is fully documented, as I said, at hp.com/go/cv. And our reference architecture actually does use a mix of direct attached storage for non-persistent VMs and our P4800 SAN storage for persistent VMs. Next slide, Tony. When it comes to the networking, one of the pieces that's very important to this is the number of wires or lack of wires used in this entire infrastructure to connect up. So we had our C7000 enclosure with 3 gigabit SAS switches and our Virtual Connect Flex 10 interconnects in there, 2 of each for redundancy. There's basically a total of 13 cables in this entire rack. 8 of the cables are used to configure the MDS 600s with redundant paths so that I can lose any one path and still have connections to my drives. 2 cables are used to stack the 2 enclosures together. 2 cables are used for redundant connection to the networking infrastructure of the lab, and we VLAN those. We'll talk about those in a minute. And 1 more cable is used to connect the onboard administrator or the management tool for managing the enclosures to our management network. So very simple, very few cables. In reality, We only had 3 cables hanging out of the top to connect to our full infrastructure. Next slide, Tony. So if you're not familiar with HP's Virtual Connect Flex 10 environment, each blade has 2 ports on it capable of 10 gigabit each. Each port can be divided into 4 possible NICs and then share the 10 gigabit speed across that. So we have, without any additional hardware added to a blade, the possibility of 8 NICs sharing 20 gigabit of performance. And we use 2 Virtual Connect Flex 10 modules for redundancy in each enclosure. So I can lose any one enclosure or any one Virtual Connect module and still have all my connections necessary. And we do this by creating everything in what's called a single Virtual Connect domain, one entire domain controlling all of the network, and 2 redundant 10 gigabit uplinks to get us to our networks. We created 4 networks within the Virtual Connect domain, one being the PBS network. This is where the Pixie boot for the VMs occurred. This network is internal to the Virtual Connect environment, does not egress the blade enclosure, does not egress the rack. We gave it 9 gigabit of speed, and as Tony will talk about, during some of the boot times, we used 92% of that strictly to boot VMs. So it's very fast, very efficient, and internal to the enclosure. We also used the other 1 gigabit of that space for our management connection to the outside world. Then we connected our public network and an iSCSI network to share 5 gig each for our upward connections. The public network was actually where the test bed sat. The iSCSI network was connected to one of our P4800 SAN storage systems, and that held the management VMs, the personalization data, and the database data. So it's kind of held all the background material that we needed. Next slide, Tony. So we talked about the DAS architecture. We really wanted to look at low cost, high performance. We had the 3 gigabit SAS switches. Each blade had in it a Smart Array 700 with a 512 megabyte battery back write cache. Each MDS is capable of holding 70 drives. So we had 140 drives available to us. Each drive is 15K in speed. These drives varied between 450 gig and 600 gigabyte. What we did is assign to each Hyper-V host that was a VDI host 5 drives in a RAID 0 configuration. That gave us the capability of having 1,500 IOPS per server. And as you'll see when Tony looks at tests, we really didn't come close to that. And that pretty much covers what we had for the hardware configuration, Tony.
Excellent. Thank you very much, Kurt. So now we're going to go a little bit more into the Hyper-V architecture and really let Gareth explain all the power that we leverage with Service Pack 1 as well as with Hyper-V for the scalability design.
Cheers. Thanks very much, Tony. Firstly, just to get an idea so I can tailor my content a little bit, hands up who was in our previous session yesterday, the Why Hyper-V for VDI session.
A little bit hard to tell with these lights.
Not everyone. Okay, so because of that, I will sort of revisit a little bit of that content, not in anywhere near as much detail as I did yesterday, because I did take up a vast majority of the session with that yesterday, but I will retouch on some points for the people who weren't in the session yesterday, which seems to be over half of you. So apologies if this is a little bit of a repetition for the people who were in that first session. Just very quickly to touch on the Hyper-V architecture, but then also to relate that back to how we architected this solution and how that relates to the scalability numbers that we got. Very quickly, what you're looking at there is a Windows server, a Windows 2008 R2 SP1 server, as it would be installed before the Hyper-V role is enabled. So as you can see there, and for anyone familiar with basic Windows and basic x86 architecture, you have the kernel running down in ring 0. It looks like we've had a little bit of an issue with the 16:9 formatting there on that from the 4.3, but that's all right. And then you have things running up in new mode up in ring 3. So then when you install the Hyper-V role, the hypervisor gets inserted at what we call ring -1. And that's made available to us by the virtualization extensions in the CPU. So the AMD V or Intel VT virtualization extensions enable that ring -1, which is where the hypervisor runs. The Windows server that you had installed then becomes what we call the parent partition. You can see the kernel of that operating system is still operating natively at ring 0, and it installs some additional components, namely the virtual machine process and the VM bus down at that level. When we install another guest operating system, whether that be a client or a server operating system, you can see again that the kernel of that operating system again is running natively at ring 0. Seems to be one of the misconceptions that people have when I go out and talk to customers about Hyper-V is that there's a conception out there that Hyper-V isn't a bare metal hypervisor. And you can see from that diagram that it very clearly is. Any guest that runs on a Hyper-V is running natively, its kernel is running natively at ring 0. There's no ring compression going on. So we'll bring in another guest. In this particular example, that happens to be a Linux operating system. We have a good support for 3 primary Linux distros, which is Red Hat, SUSE, and CentOS. In terms of that, you can see one of the things running down there in kernel mode within those guests is something called the VM bus. And that enables what we call our synthetic driver model to work. Now, it's important to understand to a degree how the synthetic drivers work and then also how that relates back to the XenDesktop architecture, because there's some best practices that I'll take you through. One thing that we're certainly very proud of is the scalability numbers that we achieved, and one of the reasons why we were able to achieve those numbers that Tony's going to go through is because of basically the very high performance that you get with Windows 7 when running on Hyper-V. 2 main reasons for that performance. Number 1 is what we call enlightenments in the operating system, which in the Linux world they call it para-virtualization. It's similar but not exactly the same thing. Basically, Windows 7 was designed from the ground up to know when it's being virtualized on Hyper-V and makes various decisions within the operating system as to what it needs to do when that's the case. The other reason we get such good performance out of Hyper-V is because of what we call our synthetic driver model. Now, as opposed to, say, an emulated or what we call legacy driver model, which we also have support for, what normally happens is the hypervisor will effectively spoof the hardware layer. So your hardware core will go down through the guest operating system, be trapped by the hypervisor on the way down. Hypervisor is going to know, well, that call's not going to work if it goes all the way down to the native hardware. It needs to be processed. It'll then go back up into the parent partition, be translated and processed down. That process isn't the most efficient in the world. There's a lot of context switching going on, and a context switch is when a process is switching between user mode and kernel mode, and there's a degree of CPU overhead when that context switching is occurring. By contrast, the synthetic drivers communicate through the VM bus, and the vast majority of that communication is being handled natively at ring 0. There's no trap or interception that needs to be done from that call via the hypervisor, because the call goes down and then is translated directly through the VM bus before it reaches the hypervisor. The result is what we call orders of magnitude less context switching going on. So the synthetic drivers are much faster, much more performant, highly efficient, and carry a lot less load on the parent operating system in terms of CPU cycles. I'm not going to read through all of those points in terms of the Hyper-V architecture. A lot of it relates to the hardware configuration of the hosts. There are a couple of points that I really do want to highlight out of that and talk to for a little bit. The first one is the second bullet point, which was a standard Hyper-V install. In other words, we didn't have to do any tuning, performance tuning with the hypervisor or with the guests, with the Windows 7 guests, to get the scalability numbers that we got. It was literally out of the box, next, finish, and these are the performance numbers that you're seeing. Doing VDI implementations in the real world, there are a couple of things that you would tweak on the guest side. Nothing much, common sense things, like disabling screensavers and those types of things where, these are things that can take cycles when they're not required. But for the most part, Windows 7 is very self-tuning and, again, aware when it's being virtualized on Hyper-V. There's very little tuning that you need to do to get Windows 7 to be very performant when running virtually. Apply that then to Hyper-V. We did absolutely no tuning of Hyper-V whatsoever in order to get these performance numbers. And in fact, we really recommend in most cases that you don't make any changes to Hyper-V at all. It is, again, very self-tuning and designed to be very, very performant out of the box. And we actually find that when people start tweaking the settings, in vast majority of cases, they're actually going to drop the performance rather than increase it. So, yeah, we didn't have to muck around with the processor scheduling or do anything. It was just next, finish, simply run up the VMs, and that was the performance that we achieved. Now actually looking at the architecture of the virtual machine, so this is of the virtual guests. Now Tony's going to go into the Citrix XenDesktop architecture for those who aren't familiar with it, but to a very brief point that needs to be understood is that unlike a lot of other VDI solutions and scenarios, the VMs don't necessarily have a local disk that they boot off. What happens is the VMs come up and can effectively be diskless. They then pixie boot to the Citrix provisioning server, which then streams the OS down instead of it actually running from disk. Now, one of the limitations of our synthetic driver model is it doesn't support pixie boot. Now, the reason for that is if we think back to the architecture diagram that I showed you a couple of slides ago, the synthetic drivers require the VM bus to operate. VM bus operates at kernel mode within the operating system. Within a Pixie environment, there's no kernel mode because there's no operating system, therefore there's no VM bus, therefore the synthetic drivers can't operate. So we have our legacy adapter for that, which has Pixie boot support. So our virtual machines that we use in this VDI environment have two NICs attached. One legacy to supply the Pixie boot and stream the operating system down, and then one synthetic network card for Windows 7 to use as its primary network interface. And one of the best practices, and again, one of the minor tweaks that we do in Windows 7 when running in a VDI scenario is you've got to make sure that that synthetic adapter in the OS is higher in binding order than the legacy adapter. The legacy adapters do carry a little bit more CPU overhead because of the amount of context switching they do. So we want to make sure we have to use them in order to stream the OS down. There's no way around that. But we want to make sure that when the OS is booted and running, that the network card that it is using is the synthetic driver to get the greatest efficiency, speed, and reduce the overhead on the host. So we made sure that that synthetic driver is higher in binding order, so it's the primary NIC that's used. In terms then of the, it's all very well and good to have the OS streaming down and have a diskless VM, but you also need a certain write disk for Windows to operate. Obviously, the page file has to go somewhere, and write operations have to go on through a normal operating system operation. So we've got really two choices there. You can either have that back on the PVS server, which is one option that we don't recommend because we want to split out that load. We want to split out that I/O to try and get maximum density. So you really actually want that write cache as a local disk that is attached to the VM, and that's what those. That's where we utilize the DAS storage of those 5 disks that were assigned to each Hyper-V host. Another best practice that I'll take you through in terms of the Hyper-V architecture, and this relates more back to the host, is one of network segregation and the amount of networks and dedicated networks that you want to have within your host. Very, very simple. For those familiar with a VMware or how to set up VMware, it's really the concepts aren't very different. We recommend to have a number of dedicated networks on the host. The first is a dedicated management network. So that's the network that the actual host runs off. It's how you patch a host, talk to your host, and it's the network that the host primarily uses. The other dedicated network that we recommend is one for the virtual machine traffic. Again, no surprises there to anyone familiar with virtual architectures. If iSCSI is being used, which in this case for this architecture it was, we recommend a dedicated network for the iSCSI traffic. And the other virtual network that we recommend that in this architecture wasn't used was in a clustered configuration. You want to have a dedicated network for the live migration traffic. Again, relate that back to VMware. They recommend the same thing in terms of their vMotion. I wanted to talk about clustering for a second because this solution didn't include clustering, and some people might be wondering, well, you know, why that was. As Tony said, we did really want to go for, you know, the most cost-effective VDI solution that we could possibly put together, and said, with that most cost-effective solution, what kind of scalability numbers can we really get? Now, obviously, SAN back-end storage can be very expensive. We wanted to try and minimize that cost and say, well, two things we wanted to say or see. Could we actually do it, number one? And two, when we did the perf testing, once we hit our maximum number of desktops, we wanted to understand what was going on from a performance perspective and where the bottleneck really was. And the most common sense thing that you would think is, well, you know, disk I/O is going to be one of your primary bottlenecks. To maximize my disk I/O, I really need a super expensive, you know, high-end SAN to go back to guarantee that throughput. So I'm just going to take a quick survey because we obviously hit a certain number of desktops and then we started to get throttled. Quick show of hands, who thinks CPU would be the first bottleneck we would hit? Okay, who thinks RAM would be the first bottleneck we would hit? Who thinks disk I/O was the first bottleneck we would hit? Okay, so I'm pretty well blinded here, but from what I can see, it seemed to be roughly 50-50 split between RAM and disk I/O. Oh, sorry, who thinks it would be network throughput? Couple, okay. Absolutely nobody for CPU. Okay, the results would surprise you, I think, because they surprised the hell out of us. It wasn't what we were expecting at all. The memory configuration was dynamic memory was used. We had a startup value of 512 and a maximum value of 1.5 gig. I'll quickly explain dynamic memory for the benefit of the people who weren't in the session yesterday. I will touch on it briefly because I could quite easily talk about dynamic memory for an hour and came close to for those who were in the session yesterday. Dynamic memory was introduced in Service Pack 1 and was really designed as a way of trying to maximize density on a host. So when we were looking into how we were going to do the memory technology on Hyper-V, we spent a lot of time talking to customers using both our virtualization technology and other virtualization technologies to say, well, out of how RAM is managed on a virtual machine, what are your top priorities? What do you absolutely want out of that feature? And really, two overriding things, or three things, but two were overriding. I mean, the first one, which is a no-brainer, which was the obvious reason, is density. We want to get more VMs on a host and maximize the hardware utilization. So that one's pretty obvious. The other ones were, which aren't, I think, so obvious. Number one is performance. We don't necessarily want to take a performance hit for running a memory technology in a slightly different way. And we certainly don't want to get into a scenario where the performance of the entire host tanks because the VMs are trying to consume or think that there is more memory than there is physically available. You can't create more memory than what's there. The box has what it has. And if the VMs are trying to consume more than that, you're going to page and performance is going to drop. And then the other requirement that really wasn't immediately obvious, and we didn't predict this, but it kept coming up, was we don't really want to have to, we want to take the guesswork out of server sizing from a RAM perspective. And this has been a problem with, you know, server provisioning really since day one, and for quite a while, really, virtualization did very little to alleviate this problem, which is, I'm building a server, how much RAM do I need to give it? I mean, with established services that are, you know, certainly with a lot of our services that are widely used throughout the world, and, you know, we've got a lot of data coming back, we've got the ability to say, well, we think for this many users, you know, this amount of resources is appropriate. And you know, it's going to vary from environment to environment, but for the most part, those numbers are pretty good, which is all very well for us because our products are very widely used and we have a lot of data at our disposal that we can use to make those determinations. But for in-house developed apps or apps from smaller ISVs where they don't have that pool of information from which to draw, it can be a very difficult thing to work out how much RAM do you need to give a server. And especially with in-house developed apps, how many times as infrastructure people have you experienced going to your app area and saying, well, how much RAM does this service need? And they go, we don't know, we haven't run it yet. And so as infrastructure guys, the thing we tend to do then is over-provision. Because we don't want to get into a situation where we haven't given the server enough memory. We don't want the performance to tank or service to be interrupted, so we tend to over-provision, which isn't the most efficient use of resources. So that was one of the primary design characteristics of dynamic memory, was we really wanted to take the guesswork out of server sizing. So what we've done is developed a system where you set a minimum value and a maximum value to the RAM that can be assigned to that server. It boots with the minimum value and then consumes that level of memory until the guest operating system determines that it needs more. At that point, RAM is hot added to the server to give it as much as it needs for that service to operate effectively. If the service use then drops down, that memory is released back into the general pool for consumption by other services. Quickly touch on the requirements for dynamic memory. Obviously, Service Pack 1 is required on 2008 Server R2, and that's required at the host level. Because of the way dynamic memory works, there's a lot of constant communication that has to happen between the host and the guest, because the guest is the one that's looking at its memory pressure and knowing what it needs. And it needs to talk to the host to say, I'm under memory pressure, I need more, or I'm not under memory pressure, and the host can say, okay, well, I'm going to pull that RAM back. So in order to facilitate that, you need to be at a supported level with both the operating system and the integration component. So the operating systems that we support for dynamic memory currently are Windows Vista, Windows 7, Windows Server 2003, 2008, and 2008 R2. You also need to be at a supported level in terms of the integration components so that those two services can communicate effectively. With Windows 7 and Windows 2008 R2 guests, they also need to be at Service Pack 1 because the integration components are built into the operating system on those platforms, so the service packs need to be aligned in order to get that communication. With down-level operating systems, so Windows Vista, Windows 2008, and Windows Server 2003, you need to be at the latest service pack levels for those respective operating systems. Then, once you've installed Service Pack 1 on the host, you then need to go into the guest and upgrade the integration components. Once those integration components are upgraded on the latest service pack on the guest, then you'll have that required communication and dynamic memory will work. A word of warning, if you enable dynamic memory on a guest and the guest isn't able to consume it because it doesn't have the integration components or isn't at the right service pack level, that VM will get the minimum amount of memory that you set. So if you're on a job and someone's complaining that their guests are running really slowly, double check that they've done what they need to do on the guest, because if they're giving it 512 or even 256 at boot up, if the guest isn't supporting dynamic memory, that's all the memory it's going to get. You can see another diagram there of the Hyper-V host architecture that was used for the testing that was conducted. As you can see, our Visio skills are absolutely second to none. I'm not going to try and read that because I'm going to fall off the stage. I think you've probably heard enough of me talking, so I'm just going to hand back to Tony now, and he's going to take you through the XenDesktop architecture.
Excellent. Thank you, Garrett. So we're going to go through what we designed from the XenDesktop side of view, including provisioning server, and kind of go over some of the practices and things we implemented as we went through and built this architecture. So what we'll look at here is a very simple communication slide. This actually is just a normal slide that dictates all the ports and protocols and so forth used. But it's also going to allow you to understand how we did a load test. If you've done a load test or are familiar with load testing, kind of raise your hand if you've done one before. All right, quite a few more than last time. So the load testing technology we did is a combination of two things. We use Citrix's own edge site for load testing. We also use an independent third-party company called Login VSI. Now, both of these together can be used at the exact same time. And the reason why we did that is because we realized that the information we can gauge and obtain out of our ICA traffic that goes back and forth is much better using our own load testing. But we also realized that VSI does a fantastic job at mimicking a user login process. Logging in, launching applications, taking a 5-minute bathroom break, coming back and going through all these particular load tests and reiterating them, looping them and repeating them until you get the necessary result that gives you the end term of number of machines you can get per host. So in this slide, you'll see we have all the ports that are listed. We pretty much start off from the beginning. At the very bottom on the left-hand corner, you see the edge site for load test set of VMs. Now, we had our series of particular blades and even 1U boxes where we had a Windows 2008 R2 on there. We had a series of Windows 7 VMs that lived on that particular blade or box. And from that box, we launched a simulated amount of sessions. Each load test consists of anywhere from about 60 to 70 to maybe 100 different VMs or independent connections we would launch from a load testing machine all the way down to that host. And we did that because we wanted to make sure we could figure out how many VMs we could get per blade, but also because we were kind of limited. We didn't have 2,000 endpoints lying around that we could fictitiously make sessions from. So we had to do it the best way that we could. And we leveraged that blade technology so we can leverage all the processing power to push those sessions as fast as we could. So as a load test starts from the bottom left-hand corner, it goes up to the top to web interface and makes its call there. The web interface load test talks to us via XML. And at that point, we enumerate the particular XenDesktop group. And once that group is initiated and enumerated, we actually start that process of logging in. So the user will log in, they'll get their desktop, and at that point, the login VSI script starts to run. Each script will run for a period of time, and once that script's done, pretty much starts over again. And we keep doing that until we get to a point where we find that threshold. What is that sweet spot? What is that magic number to where all of those variables like Garrett talked about, processor, RAM, network, disk, to where we find out this is it. This is a number to where we find out that it is the best performing number of VMs we get per host. Each of the ports that you see in this diagram here are all standard ports that are part of XenDesktop provisioning server. On the very bottom corner in the sort of purple square box, you also see the amount of SCVMM instances we use. We had 4 virtual SCVMM instances. Each one was handling an average of about 700 to 800 individual VMs we ran on there. Now, if you look on the web, you'll read that it can support 1,000 particular VMs, which is true. But we want to actually tailor that down a little bit because we wanted to figure out, well, if we put too many eggs in one basket, and because we don't have an HA design, let's figure out how we can spread that apart a little bit more. So we tailored that down just a little bit and still had really good performance from the VMM server handling all those jobs. Up at the top above that is the provisioning server port. And again, we have specific LUNs that were set up that connected from the provisioning server directly to the HP switch connect. So we had all that traffic going over a particular segmented VLAN for provisioning server traffic. So how many users can I get and how does a load test work? If I grab my mouse over here, just kind of give you an idea of what I think.
What you talking about? What you talking about? What you talking about? What you talking about?
So I bring that up because a lot of people don't really know what we're talking about. We do a test. They think, well, you just made up this number. It's fake. It's not real. And I can't really base my architecture around it. So as Arnold said, yeah, we're going to tell you what we're talking about. This is the process that the load test goes through from start to finish. A user will log in and launch these particular set of applications. Now, it's not 100% realistic, and it's not designed to say this is exactly what your applications are going to be like. It is designed to tell you what your hardware performance is going to be like, in this case, the HP C7000 blade chassis. So it's very realistic in that sense of getting you the best understanding of what your IOPS are going to be and what your processing power is going to be like. As the load test goes through, each one of these particular items are done. Word is launched, a PDF is printed, applications are unzipped. And as that process is done, we stop, we repeat the load, and we start over again. And we keep getting to that point to where we have that magic number. So once that part's done, we also go into provisioning server write cache guidelines. So this is a little bit different slide that we added in here based upon some feedback in the Auckland session. This is public information, and this is really helpful when you're trying to figure out IOPS and IOP count. Over in the bottom right-hand corner is a really simple algorithm that you can kind of figure out for estimating raw IOPS and write IOPS depending upon read. Majority of the things you'll find when it's related to provisioning server is we're pretty much 80 to 90% read and roughly 10 to 20% write. So that particular setup percentage is really important in this architecture because that saves disk IOPS. Because we're doing a lot of that work on the network, we actually can save on the back-end storage side. So it's very important when you're designing the architecture because that helps enterprises and companies save that cost. Instead of having to buy more and more storage because you necessarily may think you need it, by leveraging provisioning server, it's quite the opposite. So pool RAN's maintenance. Again, we only had one thing, if you want to call it an HA, which is where we had 2 provisioning servers that we had in the previous diagram. Now those provisioning servers were set up together in the same farm. However, they did not have a shared SQL database. Again, we didn't have a shared SQL for VMM. We didn't have anything that was shared on that side. Each was its own individual instance. So when we look at this diagram, this is pretty much a step-by-step process. If you didn't have a provisioning server that were all sharing the same virtual disk, here's how you perform maintenance and go through and modify your virtual disk one at a time. Each provisioning server had its own disk. Again, it averaged about 20, 25 gig. But you would go through this process of start to finish, pretty much 8 steps. And if you repeat this process very, very carefully and you follow it and you don't deviate away from it, you're going to have a very resilient way of designing provisioning server without the need of putting everything in a cluster. Now, a cluster does give you that HA, which Garrett talked about, and it is definitely a best practice. But if you can't do it, here's how you do it without it. So single server scalability methodology. This is the idea that we went through in terms of designing what we could get in terms of one massive super single server. Each of these bullet points are processes that we went through, and at the very top you can see we wanted to make sure that we rebooted all the guest virtual machines at the beginning to the beginning where the write cache was clean. And so everything needed to be recreated, which is pretty important because we can say that we did this test and everything was done, but then it kind of fudges with the numbers a little bit. So we wanted to push it to its very, very limits. Each user session was launched in an average of 20 seconds or 3 per minute. Now we tweak that at any given time. You can go into the load testing console, which we'll show you later, and you can set the amount of time each session will be established. For us, 20 seconds was a sweet spot because we thought that's probably a pretty realistic number in terms of how often somebody would log into a virtual desktop. The load automatically starts when the user logs in. And then the last thing at the very end is we analyze the results. We analyze results in 2 formats. We utilize the log and VSI tool, and we also leverage some of the results from the edge site load testing console. So both of those tools are used together to get that magic number, which we're going to talk about in just a minute. So we did 2 additional tests. We actually did one that we called a Red Bull setup, meaning that we beefed it up as much as we can. We gave it as much RAM as we could. We pushed it to its limit. Because as Gareth mentioned, we wanted to find out what's going to break. Is it going to be processor? Is it going to be memory? Is it going to be disk? Or is it going to be network? So we wanted to figure out, well, if we had all this hardware lying around and we wanted to build a super server, so to speak, what's it going to be like and what are the performance stats going to be? So here are some of the results from the single server scalability. This is a little bit different. We'll also have all this information. Again, you're seeing here, it's 100% published in the reference architecture, so you can read it. So don't worry about having to write notes down. It's all available. And you can kind of figure out how this would work in your environment. So show of hands again. Who thought it was a network? Not very many people, because you probably don't really think that.
Hang on, I saw one hand before. Where'd that one hand go?
I think he kind of did he put it down, right? I think he changed his mind. So 2 interfaces in XenDesktop VM, again, because it's required, one for the legacy NIC, particularly for the PVS Pixie stream traffic, and then a separate one for the HTX traffic, the normal traffic that goes back and forth throughout the day. What we thought was that we were going to flood the network. That was one of our first thoughts, because we were doing everything we could to facilitate this user workload. In reality, we did not even come close. We pushed it really hard, but we didn't get to the point where, as we looked at Perfmon stats, that the network was a bottleneck. So we pretty much X'd that one out at the very beginning. Provisioning server did what it's supposed to do, which is, again, save on that IOP traffic and really offload a lot of that, which would normally be occurring at the disk level directly at the network level. So the HP Connect switches did a fantastic job. The LUNs we had set up and the particular separate VLANs performed phenomenal. They really did a great job when we did this test. So if it wasn't network, what would it be next? We thought IOPS. Got to be IOPS. Got to be IOPS. we're doing all this particular write cache information for the provisioning server down to that HP DAS, but we were actually wrong. As we went through the test, we saw that this subsystem took a majority of the performance hit. Now again, this is early in the process, which is good, because we were expected it would get worse when it was actually quite the opposite. We had an average of 650, as you can see in the perfmon chart below, and the peak ops was 4312. So as we went through this whole entire test, we got to the consistent point where it was not IOPS. It simply wasn't. We pushed it as hard as we could. We even did more intense tests we'll show you later, where we flooded the network. We did a boot storm, and we trashed the entire demo lab by powering on 2,000 VMs at once. A complete boot storm, which in a worst case scenario, you have a power outage, what would happen and how would the disk architecture handle everything? So, who thought it was RAM? Those people who thought it was RAM, show your hand. You're wrong. Wasn't RAM either. Again, as Gareth mentioned, dynamic memory did such a phenomenal job as we went through the test. We have plenty of RAM left over on the host, 21 gig free to be exact. Quite amazing, considering that we had 144 gig on there, and an average of 135 desktops were peaking between 67 and 142 meg. Now again, that number varies because the load is occurring at different times. One particular point, a Word application is opening, maybe doing some text, doing a print job, so you can imagine those load tests are either decreasing or increasing as time goes by. So it wasn't memory. We were really, really surprised because if we look at the previous architecture we did with HP last year, maybe about a year and a half ago, on a very similar hardware architecture, we were averaging about 80 to 85 desktops per host with XenDesktop 4 and with Windows 2000 R2 pre-SP1. So from 80 to 135, it's a pretty good improvement. Pretty good improvement. So why then couldn't we scale higher? Let's find out what someone else thinks from that idea.
Guess what? I got a fever. And the only prescription is more cowbell.
It was CPU. We pushed the load so hard through this process of testing day in and day out, almost an entire month, but we really got an average of 2 to 3 hours of sleep a night, kept going back and repeating the test and repeating and repeating. And we found out because we shoved so much load into this blade and we pushed it to its limit, we actually ran out of logical processing power. That's not anything against Hyper-V, it's just we pushed so much so much work at it, it got to a point where it said, this is all I can do because you guys are coming at me so hard and so fast with such a hard load that the magic number we came up with is about 135. So single server results review. At 96 gig of RAM, not more than that, which we did in the Super Red Bull test, 123 desktops was the sweet spot. That's what we found to be the magic number, given that architecture, given that scenario. We also made sure that we put the bin file, which is needed for the shutdown of that VM, on the same LUN as a PBS write cache. We didn't segment them because we didn't have the ability to do that. We put them all in the exact same particular LUN that each Hyper-V host had. An average of the IOPS was about 650, so as you can see, it did really, really good. IOPS was not a problem with that blade enclosure as well as with that DAS. Plenty of IOPS, plenty of power. We even went as far as putting 16 disks, and I think even more, on one particular host because we were so convinced that we thought it was going to be IOPS. We kept putting more and more and more, almost designated a whole DAS to one blade. And it wasn't DAS, it wasn't SAN. It was just we consumed so much logical processor testing it. That's where the problem was that we ran across. So large scale of 2,000 desktops. What does it look like when a boot storm occurs? When you flood the network, when you do everything you can think of that would particularly happen in a worst case scenario. So in this design, we had 2 provisioning servers handling 2,000 desktops, and the average with the stream service about 1,000, give or take, per each provisioning server as it was load balanced. From start to finish, 2,350 VMs booted in approximately 23 minutes. That means that everything was off, 100% dead. Hit the power button, flood everything, let them all boot up, and this is the result.
Just wanted to interject for a second and be clear what was done there. That, in a real world scenario, you would avoid that situation like the plague, right? Worst case scenario for a VDI administrator, your worst nightmare, power outage and your entire environment goes down. You need to then get back up. Normally, you would stagger the boot of your environment because of that resource contention. The last thing that you would think of doing is actually just simultaneously booting every VM in your environment and see how long it takes. That's what we did to see, okay, in that worst case scenario, in that VDI administrator's nightmare, you know, what's the worst case scenario and what would happen?
Exactly. So again, it is worst case. It's not the best practice. We don't recommend it as a best practice because obviously you're going to get a lot of upset people knocking at your door when they can't log in. But as you can see, we still average about 100, 123 VMs per server. And at that point of where we powered on and we flooded the network, provisioning server utilized 92% of a 9 gig network traffic. Now, that's only at the point where we did the flood. As the VM started to settle down and everything started to register, it went down to, you know, a couple percent, maybe like 1, 2, 3% in terms of average network traffic that was dedicated to that virtual NIC. So you can see a boot storm, 9 gig of traffic was used for 2,000 plus desktops.
Just quickly, who's actually surprised by those numbers in terms of 22 minutes to boot 2,300 desktops from scratch? Who would have expected, if I'd told you, if I'd asked you beforehand and said, how long do you think that's going to take, would have said that it would have taken significantly longer than that. Yeah, we were pretty surprised at how fast it was as well. Quick plug for Hyper-V. One of the reasons why it was so quick, we believe, is because dynamic memory works instantly. Pretty much, you know, the second you turn the box on, dynamic memory is there and functioning and doing what it needs to do. It's extremely efficient in that way. You know, we don't need, you know, stuff to be, you know, tables to be hashed and that kind of stuff before the memory technology starts working. It's instantly there.
Absolutely. So, show of hands. I'm going to try to pull off a demo. Who would like to kind of see what this load test looks like in a real world environment? Handful. All right. Excellent. So if we can switch screens over to this PC over here and also switch the audio, that would be excellent.
Do we do that from here? Or
I think we have to do...
Oh, no. Here he goes.
Then we switch. We got to do 2 on this one. The audio should be up.
Yeah, cool. Just say if no one had put their hands up, we were going to show you anyway. So.
Yeah. All right. So we'll let this flicker for a second. There we go. Okay, so I'm actually connected right now. If you can see my screen, I'll kind of minimize this over here. There we go. It's appears to be frozen up there.
Using the mouse?
Yeah, no, I'm moving. I think the screen is frozen on the projector because we're moving down here.
Oh, okay. Yeah.
Let's switch back. Let's try to go back to 4, and let's see if it just kind of refreshes there. Yeah, definitely. I think so. I think I agree with you on that. Let's see if it's unfrozen. Yeah, I think there's something up with the projector because we're...
Kim's coming down this one as well.
Great.
Okay,
Thanks.
excellent. Yeah, we're live down here. So what we're going to do in the load test basically is log into the HP architecture that's actually in Texas, where Kirk was talking from earlier this morning. So once we're logged in, we'll go ahead and show you a little bit of the console, show you what it looks like, show you the UI of everything that we have, and then kind of show you what a load test looks like. I've got 2 extra videos as a backup that we can go ahead and play as well, and each one of those will go ahead and allow us to show you what it looked like at 120 VMs, as well as what it looks like for 2,000 plus. So each one of these things I try to record. They're kind of unedited, but you can kind of see a little bit of the video playback and kind of see how things look.
You might see how good a dancer Tony is, isn't it?
Yeah. I think right now I need to play the elevator waiting music. Yeah, for a few minutes. They sure did. They sure did. Yeah, I think it thinks we're frozen somewhere. Well, since we're waiting, I'll share something with you guys I learned last week at Tech in New Zealand. There's something that's called instant elevator music. Did you guys hear about that? So when you're kind of bored and waiting for this, I think it's instantelevatormusic.com. So if you're really, really, truly bored, go ahead and download that app, and you actually can play it right on your laptop. and it just plays the most boring elevator music you've ever heard. But it's really good when you're bored waiting for things to, kick in like this. All right, we'll give them just another minute, and if we can't get this to kick in, then we'll kind of have to stop and ask for Q&A then. One more second. Yeah. Yeah, it thinks something's up with the projector. We're live. Well, I think we'll ask questions. So we're waiting for him to fix this. Sorry about the delay. Who has any questions about the architecture and how we designed it in the sense of what else did you guys do to make this work? Did you do anything else with the provisioning server side of everything? No Citrix people can ask questions.
You mentioned about the CPU bottleneck, if you will. Was that on the PBS stuff, or was that actually on the Hyper-V hosts, or where was that exactly?
Host. That was at the host. Because we got to the point where we looked at the perfmon results over and over, and originally we thought it was disk I/O, and that's kind of where we went down this process of saying, all right, let's just go ahead and just add more disk. And we still kept getting the same result. We still kept getting about 120, 125 desktops, give or take. So at that point, we knew there was no way it could be disk, because with 16 disks associated to one host, one LUN, it can't be disk.
So do you have any scale factors for the other components that maybe you added other clusters or other stuff for the Hyper-V, how far can PBS and other things scale?
We have some other stuff. We did some other testing with Fusion I/O, which is not in there. The common questions we get asked a lot is, what about machine creation services? How does that scale with provisioning server? We did do a test. We did not see that big of a difference whether we use machine creation services. We did notice, again, because of the things that provisioning server can do that MCS can't, specifically changing where the write cache can belong at, that was a pretty big decision for us to go the PVS route, because we could split it based upon either architecture. Any other questions, guys?
Yep, one to there.
One right there.
There was one bit before you mentioned about bin files and putting the bin files in the same location as the PBS write case. Just give us a little bit of explanation about that.
Yeah, so the bin file for the save state, each one of these VHDs we also use, which we have at the end, leverages dynamic VHD, which is another thing we wanted to do that was unique. So the bin file, which is related to the dynamic memory size, it was an average about 1.5 gig. Now, it could have grown, or it could have started at 512, but we kept it at 1.5. So that bin file normally is something in the HA world you have to really be concerned about, because that's going to migrate back and forth between any host. But for this stance, we put it on the same LUN because we didn't want to carve out two different LUNs for a bin and then one for the write cache.
I'll just take the opportunity to mention a little bit about, would you or wouldn't you necessarily cluster when you're doing a VDI environment? I was out with some of the Citrix guys the other night. We were sort of discussing the pros and cons of those relative architectures. And it is an architectural decision, and we wouldn't say that one is necessarily a best practice over the other. It's really a decision point for your organization as to whether or not you feel the features or the advantages that a cluster brings you is worth the additional cost that would come with actually introducing a SAN and therefore clustering into that style of VDI environment. Really, the main advantages that we see in terms of having a VDI configuration like that in a cluster is twofold. There is a high availability aspect, but in terms of if you have unplanned downtime and a host goes down, those VMs are going to reboot, which means that you're going to lose, your state anyway. With the PVS architecture, without clustering and without the SAN, you still get the same result. So you're not really gaining anything there. But the other advantages of running in the cluster is that then enables you to have live migration, which enables two features. First one is being able to effectively patch your host infrastructure during the day with no downtime. And it also enables you to balance resources within your cluster more effectively. If you have the cluster then integrated with Operations Manager and using pro tips, then it's possible to, in terms of dynamic memory, if a box has maximum set and it's wanting to consume that memory, but the host doesn't have free memory to give it, then it can be potentially live migrated to another box that does have the free memory to give it. So you get better resource allocation within the clustered environment. Now, whether or not that's useful, I think really depends on the user workload that VDI farm is servicing. If you've got task workers who have very predictable usage patterns, and therefore those types of unpredicted memory spikes are unlikely, then you'd have to, I think, question whether or not the cluster's worth the implementation cost in that particular use case. So those are really the pros and cons, and then again, it's an architectural decision of cost and benefit and the features of the cluster and whether or not it's worth it to do it or not to do it.
Excellent. We have video back.
Hey.
Yay, we have video back.
I didn't have to dance.
You didn't have to dance, but thank you for trying to tap dance for me. I appreciate it.
We would have had a mass walkout if I'd have done that.
Yeah, no, I'm not a good dancer either, so it definitely would have helped. All right, so let me go ahead, and you can see the screen, right? All right, let's maximize this a little bit. Thanks, everybody, for being patient. Sometimes there's video things that we just can't control, and just have to work with them. They pop up.
You didn't sacrifice a goat this morning to the demo gods, did you?
No, I didn't.
Yeah, that's your problem.
It happens. So here we're logged into a particular lab. This is, again, the same lab that is used and referenced in the architecture. If I scroll down the bottom here, you can see I've got a series of VMs I'm connected to. And I'm going to kind of bring this up and maximize this big one. So here's the EdgeSite load test console. This is the console we use to fictitiously generate all these ICA sessions that went through and ran the particular script that needed to be run. Each one of these have a subset of user accounts that we're going to go ahead and launch and make this session. So from here to here, we have approximately 60 accounts. Now, 60 sessions will be generated from here, run on the particular XenDesktop host, and then run through the login VSI script. So by simply right-clicking here on this load, or going up to the top and hitting replay, the load test starts to initiate, and you can see down here at the bottom, each one of these sessions start to go through and run the actual login script. Now, what I also have at the bottom here in my laptop is a video that will go ahead and bring this up. So these are some of the things I recorded when we did this load test earlier. So I'll maximize it so you can see a little bit more. Look okay? Can everybody see that all right? It might be a little bit grainy. I'll try to blow it up as much as I can. So this is that same console you're seeing. And so as we run through this test, you can see we have a series of SCVM hosts that each have a connection for each particular subset of Hyper-V VMs. So as I run through the test, you'll see we'll right-click, we'll run this test, and we're going to actually start the load test and go through a process so you can see what that script looks like. So in this case, we had about 60, 70 machines that we were going to go ahead and launch. And the load test starts and looks just like this. The console launches. It kind of looks like a sort of ICA session, but it's a different UI and skin. And as that process kicks in, we'll try to find an active session here. And I'll go through my list. And each one of these makes an independent session. So if I scroll up, we'll find one of those recorded demos kind of right down there at the bottom. So it says replaying. This is exactly what the load test looks like. We start through, VSI agent kicks in, and all this process goes through that application startup time. So you'll see Word launch, you'll see Outlook start, you'll see this bold PDF printer application start to go. And as this goes through, this information is all being recorded and saved on a particular file share. Once the load test stops, we analyze that data with something called VSI Analyzer. And once we have that information compiled and analyzed, we go through and we find out, okay, great. So this said that at this particular amount of user load, this is what the experience was like in terms of ICA session latency, in terms of application response, in terms of network, in terms of throughput. And each one of these results, we compile at the end and find out what exactly is that sweet spot. So this is, again, a video I recorded that shows exactly how that process goes. And it's pretty much a waiting game. And I'll pause that right there. You're pretty much just waiting for that script to finish. It'll go through and keep looping, going through a reiteration of playing the script every 12 minutes, stopping, logging off, and then restarting. So let's bounce back over to number 4. So that was a load test. But how do you automate it? So we built all this stuff from scratch, but there's a catch to it. It takes a little bit of time to use a GUI. And sometimes some GUIs are not as fast as you'd like them to be. So we thought to ourselves, how could we build 2,000 desktops leveraging something really cool? It's like PowerShell. Each one of these actions or these steps are documented in a URL that I have here at the end of the slide deck. So you can actually do probably about 50 to 60% of all the work that we did for 2,000 desktops with a few clicks in PowerShell script. So I'm going to go ahead and show you what that process looks like. Again, we're all taking into consideration that, of course, you have XenDesktop installed, you have provisioning server installed, you have all the architecture components ready and particular VMs created. So let's go back and we'll go to number 2 again, and number 3. And what we're going to go ahead and do is go back and kind of show you another lab that we have set up with PowerShell running. So because we had to do a quick restart, we're going to go ahead and log into this host down here. And over inside here is a very similar architecture, just like the HP one. This is actually running here in this particular arena that was provisioned to us. So I have over here something called my Ops Manager, which is a set of scripts that I have that I can execute. Now, all these scripts do require SCVMM in order to execute. But it's pretty cool because you can do this from the GUI, and it's all can be done. But we found that we could actually build 2,000 desktops in 6 hours. Just by using PowerShell. So that's pretty impressive. If you're a PowerShell person, you really can get into the nuts and bolts of building all these desktops just by using these particular set of scripts. So the first script we're going to do is something called genvm.ps1. And what that's going to go ahead and do is generate all these VMs, the hardware profile, the settings with dynamic memory, all these variables inside SCVMM.
Nice background colors, by the way.
Yeah, thank you.
It's like being in the 90s again.
Yeah. So the first thing you're going to get is this little pop-up here talking about it's looking for a specific snap. And now you can run out that particular line of PowerShell script, but we kind of left it up there so you can see what it looks like. It's pretty self-explanatory, which is nice. You can go ahead and say, yes, I'm going to enter these parameters. And it's going to say, hey, what's the first thing you want to do? We're going to say, OK, what's the name of our host? In this case, it's E4B4. What's the name of the base virtual desktop? We'll call it XD. And we'll confirm that if we move down here and go into the VMM console, we have a series of VMs we've already created. Now, because I'm a good presenter, I don't want to crush everyone else that's on this demo land. So I'm not going to spin up 125 desktops, only because I want to make sure I'm polite to my other presenters. I don't crush their demos that are running at this exact same time, because it is kind of intense if we fire these all up at the very beginning. But if we go back here and we'll minimize the VMM console and go back to the script, the script's going to say what's the desktop you wanted to call it. We'll say XD. And what's the network for PBS? We'll say PBS. And it's going to say, what is a particular Hyper-V network? So you can see I already have a lot of this stuff pre-populated here in this command switch. So literally, I could just copy this entire line of code right here, run it right from that PowerShell command. And it's going to go through and just zoom in a matter of minutes, create all these VMs right straight from PowerShell. So I'll go ahead and just fill out the rest of this part so you can see what it looks like. Demo net. Trunk network, and then enter the locally machine those will be stored. In this case, we're putting all these particular VMs on this LUN, which is called demo VMs, and then enter the number of machines you want to create. We'll just say 5 to make it simple, and then enter the number starting it. You want to start like the machine name at _1 or the number 1. And now here we can actually append dynamic memory variables right directly into this PowerShell script. So we can actually build this all for us on the fly. So we'll say we'll start at 512, and we'll put a memory to assign at 1536, and then number of CPUs, which will be 1, and a percentage of memory, do the default of 20, and then the weight of 5,000. And then we put in our credentials to make sure that it knows exactly who we are. And then we hit enter. And we confirm everything at the end. So this script's going to go and execute and go through a process of creating a series of VMs that are going to match this particular name directly here into SCVMM. So it's going to be creating XD001, and it's going to walk through and create each one of these directly here into SCVMM as that script executes.
I'll just make a comment there on what Tony just showed you, and
And I already created some of these. So these are already duplicate because I already have those in place.
Yeah.
But
name's incorrect,
that comes up because they're already there. So I could have called it XD2 or something like that.
Yeah. The SCVMM, and in fact it's a way that we're going with a lot of our products now. It's the direction we're heading, is everything is based on PowerShell. SCVMM, basically when you use the console, it's actually writing a PowerShell script under the covers to execute that work. So in a lot of ways, the UI is actually a convenience, but it's actually PowerShell that does all the work. So there's a very, very handy feature in VMM where once you do something through the GUI, the last stage before you hit finish to commit that action, there's actually a view script button. You hit that and it'll show you the PowerShell script that's been written under the covers to actually facilitate that work. And some of the more mature VMM implementations that I've seen actually do very little through the UI. They actually do most of the work through automation and PowerShell. And that's really the point that we were getting to when we built VMM, was to trying to get people to that more mature implementation model where you're doing a lot of automation and doing a lot of things through scripts. And the show script button through the UI gives your administrators a very easy way of starting to get their feet wet with PowerShell and starting to learn it. Hit the view script button, you see the script as it was written by VMM. If you need to automate that task, if it's a repetitive task that you do all the time, like creating virtual machines, you can simply grab that script and then with a slight amount of modification and make it reusable.
Exactly. So each one of these steps, we've broken them down to separate scripts because you may want to modify these at any particular time. So the next one we could say would be list VMs, and that's going to go ahead and produce us a list of all the VMs that match this particular name and populate and push those lists down to the bottom. So this list is important because we need this list to go ahead and take that information from SCVMM and then import it into provisioning server. So our
Snap-in's not running.
Yeah, that's got the couple typos probably in there. Once we have that list created, we can now go into a provisioning server and actually create what's called a PVS file. In order to make all these desktops available for provisioning server, you have to actually either use a XenDesktop setup wizard or have a particular file, in this case, common delimited file, where we can take it and import it directly into PVS. So what this script does is goes ahead and takes all this information, dumps it out into a particular file, and then gives us the ability to go ahead and create all this particular information here from those machines that match that name and import that directly into provisioning server. So each one of these are pretty cool because I can automate and do this start to finish without having to actually go through the GUI and do all the work I would normally have to do. And it's quite fast. These are all public PowerShell scripts. You can modify them, you can tweak them, you can put them together, you can do whatever it is you'd like to do with them to help make a lot of this stuff automated. We also made some other ones here, as you can see, that actually allow you to go ahead and rechange dynamic memory. So let's say you built 2,000 desktops, but you realized 512 wasn't the best starting point. Maybe this subset of users needed a little bit more. By running this PowerShell script here, I can go ahead and look for this particular name of VMs and assign all these variables I did in the original script on the fly and put them right into the VMs. So it's all automated. You can change these things on the fly when you're making a massive amount of changes. So once all that's done, we simply go back here and we take this information into provisioning server. And we go into our particular collection here. And we go into target device, we import. And this is going to allow us to go ahead and select that particular CSV file that we created before, which is right there. We'll click open. We'll click next. We apply this template here because this template already knows where my virtual disk resides. And then we uncheck some of these additional ones that we don't need right there. And then click finish. At this point, everything's been imported to provisioning server. We've done all this work from PowerShell and pretty much have not realized or not needed the ability to use the GUI because it's done. And you can see we click done and there's all our virtual desktops. So we created them with PowerShell into VMM. We assigned dynamic memory. We added the provisioning server write cache. We took all that information, exported it into a CSV file, and at the end you have all this done with just a matter of a few PowerShell yes or no answers that you need to provide us some questions. So it's pretty automated, really simple to replicate, and easy to do. Let's go back to 4. And so that concludes that part of the demo, but I have one last thing to show you. Because I got special permission, I can show you what XenDesktop 5.5 looks like with VMM 2012. And we're going to kind of fast forward through some of this video. What you're seeing here is us creating a series of desktops directly from the XenDesktop console. So we're going to go through this process and create these using machine creation services. Now, obviously, we're going to be having more features for provisioning server, as well as leveraging PBS for VMM 2012. But here you can see we just got a separate set of OUs. We're going to create these particular VMs. It's going to go through like a normal person would, create all those VMs, stick them in a separate OU. And then once that's done, we pretty much have the particular set of desktops created. They're ready, they're in VMM, and they're ready to go. So recapping everything, here's what we learned from this particular presentation. All these are different things that are available. Tuning SCVMM, definitely highly recommend that in terms of modifying that and optimizing as much as possible if you like to. Making sure you change your global static range pools, because when you have two SCVMM servers, they don't necessarily talk to each other, know which MAC addresses to dish out. So there's something you definitely want to change. And then make sure you're patient with jobs, because VMM processes all these jobs. Some people get a little patient and start to go back into Hyper-V and shut VMs down when you really don't want to do that. You want to let the jobs finish so that you get the VMs created successfully and registered successfully inside XenDesktop. All these PowerShell scripts, again, are at this link below, so you can go ahead and use this presentation, download it, and get access to all these scripts that we created for you. And that concludes everything we have. If you have any questions, we're just out low over our time. Please come up, and we'll be happy to answer any of those questions you may have. Thanks, everybody.